Hello, so welcome again. Now, today we are going to continue and study about functions and continuity. And in this chapter, we shall understand about how to deal with certain kind of functions and how to define their continuity and stuffs like that. So, let me give you the heading first. So, what do we mean by functions in multi-dimension forms? Because in one dimensional we knew that a function f from R to R can be defined as some f of x, where f of x belongs to R while x also belongs to R, right? Examples might include f of x equals to cos x, sin x, maybe x square plus 2 and stuff like that, okay? But when we are talking about multivariable functions, we would like to extend our dimensions, and we are going to talk about Rn and Rm, which is basically n dimensional Euclidean space and mth dimensional Euclidean space. So basically, a function from R to the power n to R to the power m, sometimes called a vector valued function of n variables, is a rule which associates to each point in Rn some point in Rm, right? So a function from R to the power n to R to the power m assigns to each point in Rn some point in Rm, right? So this is how we define functions, and obviously this means that we have a function which goes from R to the power n and it goes to R to the power m. This also means that the domain of f is basically R to the power n, and it also means that f of R to the power n is a subset of R to the power m, because it not necessarily it is equal to R to the power m, but it is obviously a subset of R to the power m, because that's where the output goes. Now if f is 1 1 or injective, only then is f of x R to the power n equals to R to the power m. Basically, sorry, if it is onto, and if it is bijective, obviously that is true. Now we shall talk about limits, because obviously we are trying to find out continuity at a certain point. So what did it mean in one dimensional form to have a continuity? So when we said that limit extends to a, f of x equals to b, this meant that for every epsilon greater than 0, there exists a delta greater than 0, such that for 0 less than mod of x minus a less than delta, we have mod of f of x minus b less than epsilon for all epsilon greater than 0. So this was the definition of continuity in one variable case. Now in two variable cases, we shall find out that there are many ways to find out if a function is continuous or not. So we will be trying to state them one by one. So let's see the first one. If to the power m and u belongs to R to the power m is open, then if f inverse of u is open, then f is continuous. and this is true whenever you have any open set U which is a subset of r to the power n. So for every open set U for in r to the power m, we have that U is open, then and also f inverse of U is open, then we can conclude f is continuous. That is one way. But obviously this happens only when f goes from like r to the power n to m, but it may not be true because then we have a general theorem for it. We may have a slightly lesser domain or codomain, but then that theorem does not apply. Rather, the general version applies, which says that if A is a proper subset of r to the power n and f goes from A to r to the power m, is continuous if and only if. So it is continuous if and only if for every open set U belongs to basically U subset of Rm. Basically there is some open, there exists some open set V which is a subset of r to the power n such that f inverse of U should be V intersection A. So this is the theorem. So if there is a function f which goes from A to r to the power m, where A is just a proper subset of r to the power n, then that function is continuous if and only if for every open set U which is a subset of r to the power m, there exists some open set V which is a subset of r to the power n such that f inverse of U is equals to V intersection A. Now this means that obviously if we were to prove it, well, if f is from A to r to the power m, the inverse would be from r to the power m to A, right? So f inverse of U is basically where, since U is a subset of r to the power m, f inverse of U will have its the output of f inverse of U is obviously in A. So if there is an element belonging to f inverse of U, then we can say that f of A will also belong to U. Now since U is open, there is an open rectangle B such that f of A belongs to B, which is a subset of U. Since f is continuous at A, we can ensure that f of x belongs to B, provided we choose x in some sufficiently small rectangle C containing A. Do this for each A belongs to f inverse U and let V be the union of all such C. Clearly f inverse U is V intersection A, and this is how we can visualize the theorem. So this is basically how we want to understand this continuity theorems here, and for that we can have a few solutions and few problems as well which we can solve. So let us see those problems one by one. So let me write it down. If f goes from A to r to the power m and small a belongs to capital A, show that so this means that we are going to say that this function, a function from A to r to the power m, is only only continuous only if all the component functions, all the m component functions that f has are continuous at a as well. So what it means is that you understand that here x belongs to a and b belongs to r to the power m, right? So naturally, since f of a is a subset of r to the power m, we have f of x for all x belongs to a. F of x should be a m component function, right? So f1x, f2x, and all the way up to fnx. Now that is why what we want to prove is that those limits are also true. So we are going to prove two parts. So first the if part. So we assume limit x tends to a, fi of x is bi. Okay, where b is like b1, b2, b3 all the way up to bm. Then what we can understand here from this is from the this is like single variable calculus, we can say that for every epsilon by root m greater than 0, why the root m is there, it's something that we can do by back calculation. So we'll see why it is that there exists delta I greater than 0 such that minus bi is less than epsilon by root m for all x belongs to a and 0 less than norm of x minus a less than delta 1, delta I actually for I, right? And if you write this one for all delta i's, what you can do is put delta equals to minimum 1 less than equals to I less than equals to m delta I, so that all those statements are valid equivalently. And you can say that therefore for all x belongs to a and 0 belongs to x minus a's norm less than delta, we have norm of fix minus b is less than epsilon by root m, right? It should be bi actually. Bi is a component function. So this means that this norm can be evaluated. So what we can prove is this. Then for every x belongs to a such that 0 less than norm of x minus a less than del. Now we can come back to the original function f of x minus b. Now this function basically means that this is subtraction of two functions. It's basically f1x minus b1 and stuff like that. So the norm of it would be just root over of summation from I equals to 1 to m fix minus bi squared. And what you can understand is this norm, this fix minus bi is less than epsilon by root m. We can find out that this is equals to I equals to 1 to m epsilon square by m, right? And this becomes, since this summation is just m, so it becomes epsilon square, which becomes epsilon. So therefore fx is continuous at b, therefore limit x tends to a f of x is equal to b. So this is how we prove the if part. So let us revise it once again what we did. So we basically had a function f from a to r to the power m, and a small a belongs to capital A, and we needed to show that limit x tends to a, f of x equals to b, if and only if limit x tends to a, the component function is equal to are also continuous to the component functions of b, right? Now, for x belongs to a and b belongs to rm, we understand that if we already assume that the component functions are continuous, and we said that for every epsilon by root m greater than 0 there exists some delta I such that the component functions are continuous. Because it is already given, we can conclude this directly from the statement that f I x minus b i's norm is less than epsilon by root m. In this case, the norm is just the absolute value because these are single variable functions, and we assume 0 less than uh, norm of x minus a less than delta I. Now notice that x minus a has to be taken in norm because x is basically a function of element of a, and a small a is an element of capital A as well, and we do not know if capital A small r is like r or not. It might be multidimensional, right? So we put, because it was for all I, we can put delta equals to minimum of all those delta I, so that this statement is in general true for all the i's. And then for all x belongs to a and 0 less than norm of x minus a less than delta, we had like f I x minus b i's norm less than epsilon by root m, which was the statement. And now for every x belongs to a and 0 less than x minus a less than delta, we had the actual function f of x minus b's norm equals to root over obviously summation of I equals to 1 to m f I x minus b I square less than I equals to 1 to m epsilon square by m, which turned out to be epsilon, which means limit x tends to a, f of x is b. Now to do the converse part, we suppose first that limit x tends to a, f of x equals to b. Then by the definition of continuity, it says that then if for every epsilon greater than 0, then for every epsilon greater than 0 there is a delta greater than 0 such that norm of fx minus b is less than epsilon for all x belongs to a and 0 less than norm of x minus a less than del, right? But this also means then for all I belongs to 1 to m, we see that modulus of fix minus bi is simply less than the norm of the whole thing, because this is just one component. It must be less than or equal to the whole thing, which is less than epsilon for all 0 less than of x minus a less than del, right? This means that therefore limit x tends to a, fi of x equals to bi, thus proved. So it was a pretty well formed exercise actually. Now problem 2 is something like before as well, so it's just a small exercise corresponding to what we did in the first one. Let me write down the problem. So this should be a small a actually. So prove that f from a to r to the power m is continuous at small a if and only if each fi is. So what we are trying to say here is f is continuous at small a if and only if limit extends to a f of x equals to f of a, right? So because since we understand the continuity part, we can say that if f is continuous at a, we can assume f is continuous at a, then limit x tends to a, f of x is basically f of a, right? And it follows from the previous part that whenever this happens, we understand that limit x tends to a, fi of x is also equals to fi of a for all I belongs to 1 to m. From previous exercise, right? From previous exercise we can conclude that, therefore it is true. So this problem is just an corollary, moreover, that you need to understand that whenever if b is not given, we can instead use f of x equals to f of a, right? Okay. So prove that a linear transformation t from r to the power n to r to the power m is continuous. Now a linear transformation is of course a linear operator which has the properties that if f of ax plus let's say it by t of ax plus by is equals to a into tx plus b into ty, where a and b are real numbers or the field from which t is taken. So here we have to prove that a linear transformation from r to the power n to r to the power m is continuous, and it's in general, which means all linear transformations from r to the power n to r to the power m are continuous. And to prove this, we obviously have to understand that general statements needs to be proved. And we remember from the last exercise, we also knew that linear transformation is also bounded above multiplied by its norm at the point it is considered. So taking any a belongs to r to the power n, we see that there exists m greater than 0 such that tx minus ta equals to t of x minus a is less than equals to m into norm of x minus a, because we know that the linear transformation at any argument is less than equals to some capital M times the norm of the argument. That is how it was bounded above, right? So from this we can see that for every epsilon greater than 0, there exists a delta greater than 0 such that 0 less than delta and tx minus ta. So the norm of this is less than equals to m into norm of this, and since this is less than delta, this is less than equals to m delta, right? So choosing delta, so what we can do here is choosing epsilon equals to m delta, we have tx minus ta less than epsilon for all 0 less than norm of x minus a less than delta. Okay, so we can like choose this delta as epsilon by m, and that would be it. So this means that obviously limit x tends to a, t of x is equals to t of a, and thus the answer is proved. So we used something from the previous exercise to prove this exact thing. Okay, so like this kind of problems might be not very tough to solve, but then again we can solve it using our definition of limits and single variable limits. So I'll let you know, I'll drop in a video for limits at the end so that you understand how to do the limits. So introduction to and some solved problems in one variable limits will be there, so that you have an idea of how to solve this kind of problems. So limits, obviously as the name suggests, you might have also seen it before, limits are a way to find the limiting value of a function at a certain point. So what I mean by this, when I write lim, it means limit, and under it I have to write the variable and the value it goes to. So this expression right here would mean limit x tends to 2. So theoretically it means this. So in a general way, when x tends to 2, it always means that x not equals to 2. Okay, but it just goes towards 2. So if you can imagine the number line right here and 2 is somewhere around it, let's say this is 1.5 and let's say this is 2.5, then the variable x assumes on these values very close to 2 but never 2 from the left hand side, and it also assumes values from the right hand side very close to 2 but never 2. So the values that this variable assumes goes towards 2 infinitely closer but never actually close enough to be equal, right? In a sense that we can actually evaluate the following thing. So how do we actually evaluate limits? So first we write this, and the question could be something like there could be an expression like this, f of x. Okay, now if this is the limit problem we are trying to evaluate, it will have an answer, limit x tends to 2 f of x. Now the answer could be f of 2, you just put in the value of x here only when f of 2 exists, but in more cases than none f of 2 will not exist, or putting just the value of the limit will not work. A common example would be like this, limit x tends to 2 this. So as you can see, if we were to put the value here, it will give us 4 minus 4 by 2 minus 2, or 0 by 0, which is practically undefined. It doesn't make any sense at all. Okay, so therefore like this kind of problems need to be handled in a bit more subtle way. What we do here is this: we try to eliminate the factor that's making these zeros come, right? We try to eliminate the factor that makes the function undefined. So here this is the factor, and if you can see, the numerator can actually be factorized, right? How? Limit x tends to 2, x plus 2 whole into x minus 2 divided by x minus 2. And now if I were to say that I can cancel the x minus 2's off, it wouldn't be illogical to ask that why can we cancel them off, because they're literally zeros, right? Because x tends to 2 but then x minus 2, if I put the value of 2, it becomes like 0 by 0, and you cannot cancel off zeros. That would be doing literally the same thing, but in fact we can. This is because, as I said you in the earlier part of this video, that whenever I say x tends to 2, this always implies that x is not equal to 2, right? This means that inside the limiting expression, when I'm not putting the value, inside the limiting expression, we can always cancel off the x minus 2's, because x minus 2 is very close to 2 but never 2, so x minus 2 is never 0 actually, because we still have the limit thing on, right? We have not exactly put the value. At the end we put the value of x into the expression, back into the expression, when the function is defined at that point. But before that, whenever we encounter something like the zeros, like this x minus 2 divided by x minus 2, where both the terms actually evaluate to 0, if we put the value, you can cancel them off, because inside the limit they are not exactly 0, they are close to 0 but not 0. So this gives you limit x tends to 2, x plus 2, right? And now, since this is defined at 2, this is not like undefined or infinity or anything like that, we can actually use the value of x to find out this is 2 plus 2, which is 4, which becomes the answer. Okay, so this is a common way to find out limits. And now let us introduce to some of the more basic limits that we shall be encountering. Firstly, a note on this regard: if you have limit x tends to a, where a is a real number, and x to the power n minus a to the power n by x minus a, limits of this form have a general answer, and it is n into a to the power n minus 1. Okay, as you can see in this example, where we had like x tends to 2, x square minus 2 square by x minus 2, here n was 2 if you can match, and a was 2 as well, so the answer should have been 2 into 2 to the power 2 minus 1, which is 4. So it's a general answer. And why is it true, I'm not going to explain right now, because for that we need the factor theorem, or we can use the derivative, which is the L'Hopital's rule, which we shall learn after we learn a bit of derivatives. Before that, it's really hard to evaluate harder limits without using the derivative. So this is the basic which we need to learn here about this formula, and let's do a few examples about this. So example 1 would be limit x tends to 2, x cube minus 2 cube obviously by x minus 2. This is a direct application. And example 2 would be something like this: 27 divided by x square minus 9. Now let us do the problems one by one. Solution to 1. This is a direct application of the formula, so this is just for practice that you remember what we are doing. So x cube minus 2 cube divided by x minus 2. So you can see the n is 3 here and a is 2 here, so it should be n into a to the power n minus 1, right? This just evaluates to 3 into 2 square, which is basically 12, which is the answer. Now this one is a bit easier, but the next part could be a little bit more tricky, because it's not really the formula you think it is, because limit x tends to 3, x cube minus 27 divided by x square minus 9, right? So like before, we can also see that here if we put the value of 3, it becomes like 27 minus 27 divided by 9 minus 9. But we cannot let that happen, because that would just give you a 0 by 0, of course. But we do know that this is in a similar form as to have the formula we just learned, because this can be written as x cube minus 3 cube divided by x square minus 3 square, right? Now one thing you need to know is, whenever limits exist, different portions of the function can be evaluated separately in multiplication and division form, and also in addition form. Okay, so what does this formula is missing? If you look at the formula which I have defined here carefully, you see that we have limit x tends to a, x to the power n minus a to the power n divided by x minus a, right? We are missing that portion. So what portion do we need here? If this limit were to work, we would need a divided by x minus 3, wouldn't we? But how do we get that? Well, luckily there's two of those, and obviously you need two 1 by x minus 3's, right? So if you divide up and down by x minus 3, what you get is this. This is called adjustment. So in more cases we would actually adjust the limits to a known form like this. We just divided up and down by x minus 3, which is obviously within the rules. And then again you can divide by x minus 3 because x tends to 3 implies x is not equals to 3, right? This is very important because otherwise there would be no justification of dividing by 0, right, if x were equal to 3. Now these are two separate limits, right? And you can see they clearly form in the pattern of the formula we learned, but there are two limits and they are in divide form. But as I said, as long as the individual limits would exist, they can be evaluated separately. So basically, since both of these limits exist, it can be written like this. Divided by this. So this would give me like limit x tends to 3, x cube minus 3 cube divided by x minus 3 whole divided by limit x tends to 3, x square minus 3 square divided by x minus 3, right? So this would give me the above portion would be 3 into 3 to the power 3 minus 1, and this one would be n here is 2, so 2 into 3 to the power 2 minus 1, right? So let's evaluate how much that is. This is 3 into 3 square, this is 2 into 3, 3's cancel off, the answer becomes 9 by 2, correct? So this is the answer to our question. So this was a bit tricky, but what I wanted to introduce to you was this concept of adjusting. So we will find limits where we might have to introduce something new in order for it to work, like we just did the 1 by x minus 3 thing here in both the numerator and the denominator. But often more than not, we might have to introduce some things by known formulas we already know, and we have to make them work like that, right? We have to make them in a form we already know. That's what I'm trying to say. This basically is the first formula that I would like to show you, and let's go on to another one. Another formula is limit x tends to 0 ln of 1 plus x divided by x equals to 1. So this is another formula. Here ln means the natural logarithm, and we are saying that as x tends to 0, the limiting value of logarithm of 1 plus x whole divided by x is equals to 1. Now, how to adjust? That's what I'm trying to make sense here. So let's see. How do we do that? If we had the limit like this, limit x tends to 0 ln of 1 plus 2x whole divided by x, how would we evaluate this? Because this exactly doesn't go with our formula, right? But you need to understand clearly what it means here. It means that when the variable goes to 0, if you have logarithm of 1 plus that variable which goes to 0 divided by the same variable which goes to 0, this particular expression amounts to 1. Okay, so it really means here that limit x tends to 0, if you have a 2 here and you just write it like this, this expression in the limiting value should go to 0 or should go to 1. Why is that? Because see, if x tends to 0, you can treat this as an equation here, so 2x will also go to 0. Okay, this is entirely true, because x keeps on decreasing and goes to 0, so obviously 2x will also keep on decreasing and go to 0, maybe at a slower rate, but yes, it will go on, right? So this means that we can write this limit as 2 into limit. Even if you want, you can just substitute for 2x as y and then write y tends to 0, or you can just simply write x tends to 0 or even 2x tends to 0, which you should not write once you get enough practice, but for now it's okay. It will give you 2 into 1, which is 2, right? So I hope the idea is clear, that how to actually do these adjustments like we did here and like we are doing here. Let's go to another one. Number 3. We can write another formula here. Limit x tends to 0, e to the power x minus 1 by x is equals to 1. Well, this is one of the same things. This is another formula, and obviously if you had something like limit x tends to 0, e to the power 3x minus 1 by 2x, let's say, and if we were to evaluate this, obviously we need to get it to this form. Okay, so the power of e and the denominator must be same, and we have the minus 1 as well, so this should be 1 if given a proper adjustment. So firstly, this 1 by 2 here is the constant. We can take it out and write it as limit x tends to 0, e to the power 3x minus 1 by x, and then we can have a 3 here, so that we do a proper adjustment by making the denominator equal to 3x, and this shall give you 3 by 2, because this portion is just 1, right? Right. So I hope you get the idea. Now it's time to prove two of these things. So proof 1. We are trying to prove that limit x tends to 0, ln of 1 plus x by x is equal to 1. Okay, see, this is not a very easy proof, but we can walk our way through it. I'll just show you how. Well, first of all, x tends to 0, so this obviously means that we have that mod x less than 1, since x tends to 0, so x is in the close neighborhood of 0, right? So it's like an epsilon distance, which is very small. We can consider as small as we want to be, and it's in that distance in between 0. So basically x lies in an interval like this, where minus epsilon to plus epsilon, and epsilon is sufficiently small. Right? So with this expression in mind, what we can do is we are trying to find a series representation for logarithm of 1 plus x, natural logarithm in fact. How do we do that? Not yet, but let us try to use the theory we have used earlier, which is the Taylor series, right? But in this case we need to find it near 0, so we can use the Maclaurin series directly. We remember that Maclaurin series for fx is given by f of x is equals to summation n equals to 0 to infinity nth derivative of f at the point 0 divided by n factorial into x to the power n, right? And here we have mod x less than 1, since we are trying to find it for logarithm of 1 plus x, which is only defined for minus 1 less than x less than 1. Okay, So we need to, the only term we need to find is the nth derivative at the point 0. So let us begin and try to see what happens. So firstly, f of 0 should be ln of 1 plus 0, which is ln of 1, which is 0. So the first term is 0, like the 0th term is 0. Okay, f dashed x in fact would be 1 by 1 plus x, and this would mean f dashed 0 should be 1, right? F double dashed x would be minus 1 by 1 plus x whole squared. So f double dashed 0 should be minus 1. Again, f triple dashed x should be 2 by 1 plus x whole cube, and this would mean that f 30 is 2, right? So this is going to give us a pattern very soon if we just continue it for like 3 to 4 terms, because I do not really want to indulge you with the nth derivative formula directly, which we can calculate directly from here, but let's save that for the derivative portion. So f4 of x again would be minus 6 by 1 plus x whole to the power 4, or in other words, this is just minus 3 factorial by 1 plus x whole to the power 4. So this was give us f40 equals to minus 3 factorial. Let us do 2 more terms. f5x would then be the differentiation of this, which would give you another minus, it will make it a plus, and it will be 4 factorial by 1 by x to the power 5, which would give me f5 of 0 equals to 4 factorial. And similarly, f6 of x should be minus 5 factorial, judging by it. It should be minus 5 factorial by 1 plus x whole to the power 6, and this should be equals to minus 5 factorial, right? So as you can see, for the even number of even order of derivative, we have a negative factorial, 1 less than it, and for the odd we have the positive factorial but 1 less than the derivative. So we can write that ln of 1 plus x, by the Maclaurin series definition, it should be f0 plus x into f dash 0 plus x square by 2 factorial into f20 plus x cube by 3 factorial into f30, and so on, right? Now once we start putting in the values, we see that f0 is 0 and f dash 0 is just 1. For the even one it's negative, if you remember, so it's not plus, it's like minus x square by 2 plus x cube by 3 factorial into 2 factorial minus x to the power 4 by 4 factorial into 3 factorial, and so on. Remembering that 3 factorial is just 2 into 3 into 2 factorial, so the 2 factorial will cut off and 3 will remain. Similarly here, 3 factorial by 4 factorial will give you a 1 by 4. Continuing in this way, we get the series as x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus x to the power 5 by 5, and so on. So this basically right here is the Taylor series expansion for log of 1 plus x at the point x equals to 0. Now we want to see that in the limiting case, we were trying to prove that limit x tends to 0, ln of 1 plus x by x, right? Now let us write it under, because the series could be a long shot. So we can use the series definition here, and we can write it as 1 by x into x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4, and so on. Now since we know that x tends to 0 means x is not equal to 0. We can divide by x and we can find that the answer is 1 minus x by 2 plus x square by 3 minus x cube by 4 and so on, right? Now, as I know that we can always put the value of the limit whenever the function is defined. Here we just have a bunch of plus and minuses, obviously infinitely many of them, but we can write this as 1 minus limit x tends to 0 and then x by 2 minus x square by 3 and so on. Okay, but all of these terms will be 0 because when you put in x equals to 0, doesn't matter how many of them are infinitely many zeros add up to zeros only. So the answer would be just 1 minus 0, or which is 1, and thus we have proved our limit, right? A similar argument can be made for the next one where we are trying to prove this, where we are trying to prove limit x tends to 0 e to the power x minus 1 by x equals to 1. So starting with e to the power x equals to 1 plus x square by 2 factorial plus x cube by 3 factorial and all the way, we can see that if we just take the 1 on the left hand side and divide by x, what we get is this: 1 plus x by 2 factorial plus x square by 3 factorial plus so on. Now if you apply limit to both sides, what you get is this: you get limit x tends to 0 e to the power x minus 1 by x equals to 1, since it's a constant, plus limit x tends to 0 x by 2 factorial plus x square by 3 factorial and so on. But then again, all of these terms are 0, so the answer should be 1 plus 0, which is 1, right? I have used this definition because I have already showed you how to get the Taylor series for e to the power x in the previous videos, so I just used the result directly. If you really want to revisit, you can just have a look at the previous videos to see how this was derived. I've done it in every step possible. Now this gives the proof for two of our formulas which we learned, and for the first formula as well, we can actually give a outline of the proof of limit x tends to a x to the power n minus a to the power n by x minus a is equals to n into a to the power n minus 1. So this proof is generally given by factor theorem. So let me state the factor theorem here. It's an important result, so if you want you can note it down. The factor theorem says that x to the power n minus a to the power n is equals to x minus a into x to the power n minus 1 into a plus x to the power n minus 2 into a squared and all the way up to I do not think this was there, yeah, x into a, and the last term would be a to the power n minus 1. Yeah, this is the factor theorem. So it factors like expressions of the form x to the power n minus a to the power n. So if we were to use this factor theorem, we could easily see that limit x tends to a x to the power n minus a to the power n divided by x minus a would be equal to limit x tends to a x minus a into x to the power n minus 1 plus x to the power n minus 2 into a and all the way up to a to the power n minus 1 divided by x minus a, right? Now since I have already told you x tends to a means x doesn't equal to a, so we can carefully cross this off, and we are left with limit x tends to a x to the power n minus 1 plus x to the power n minus 2 into a plus x to the power n minus 3 into a squared, and all the way up to a to the power n minus 1. Now, putting the value of x, because now this expression is completely defined and it's a polynomial, we see that it is equal to a to the power n minus 1 plus a to the power n minus 2 into a plus a to the power n minus 3 into a squared, and all the way up to a to the power n minus 1. Simplifying, we would get a to the power n minus 1 plus a to the power n minus 1 plus a to the power n minus 1, and all of the terms would be a to the power n minus 1. And how many of them are there? There are n of them, because see, here the power starts from a to the power 0, here the power ends at a to the power n minus 1, so from 0 to n minus 1 inclusive there are n terms, right? So it becomes n into a to the power n minus 1, which is the answer, right? Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.